The first thing we need to wrap our head around today is the idea of a flux integral. So far, the only integral quantity that we associate with a vector field has been circulation. And circulation gives us a measurement of to what extent does my vector field and a parametric curve go in the same direction as one another, in which case the circulation would be positive, or maybe in some places those are aligned oppositely from one another. So my vector field and my parametric curve might be kind of opposed to one another, in which case the circulation would be negative. Or in the case where the circulation is zero, that means that at least on a net basis, the vector field and the parametric curve are perpendicular to one another. And because of that relationship in circulation, we end up using a dot product to find the parallel component of a vector field that goes in the same direction as the velocity vector of our parametrized curve. What we want to do today is we want to take all of those notions and just turn them 90 degrees. And what I mean by that is, instead of looking at circulation, which would be to what extent does a vector field go in the same direction as a curve, and count that as being something positive, what we want to do today is just to take and turn 90 degrees and ask, to what extent does a vector field slice through my parametric curve? And when it slices exactly through at a 90-degree angle, we want to count that to be large and positive today. And we want to count the situations where my vector field and my path go in the same direction. We want to count those as being zero. Okay. So what we're getting is a measurement of to what extent does a vector field flow across a curve. So that if a vector field is exactly flowing along a curve, the answer would be zero. And then if it flows directly perpendicularly through the curve, then the amount of what we call flux, which is the flow through something, would be maximized in that situation. So when we get to talk about surface integrals tomorrow and Friday, a good analogy would be we put a net out in the water, right? And that net forms the shape of some surface. And then we're sort of asking how much water is flowing either into or out of that net, depending on how we orient the surface. So just like a parametrized curve has an orientation that's associated with its velocity vector that tells us which direction the curve is flowing in, we also would specify an orientation for a piece of surface that tells us which direction are we going to consider to be the positive direction for our flow, for our flux through the net, right? And you can imagine that if we just put like a flat planar net down in the water, we could choose either direction as being the positive direction of the flow, just depending on how we want to make that measurement. So we get basically a coin flip for an oriented surface. And it's actually an interesting question about what an orientable surface even is in the first place. Not every surface in 3 dimensions is orientable. Think about a Mobius strip as an example of something which cannot be oriented. We're not going to look at those. We're going to look at just surfaces which do have an orientation. And so we'll just have two choices. Should I orient it with a normal vector facing this direction, or should I orient it with a normal vector that faces in the opposite direction? So when we look at that in the 2-dimensional case, we're also going to likewise have 2 different choices of orientation, and we're going to see that happen as part of our preview activity for today. So the preview activity is going to have us thinking about just what is the idea of the net flux of a vector field into or out of a surface. The way that the authors of our book put it is that we're sort of looking at to what extent does a vector field sort of have little sources or sinks inside of it? How does it change strength as we go from one place to another place, right? That if I were to place a little blob of ink down into this vector field, would that blob tend to spread out if it flows along the vector field? Or would it tend to get smaller? Would the ink sort of get compressed in on itself by this vector field? And so those are the ideas that the authors want to get us thinking about. And so in our first activity, we're being given 3 different vector fields, first as pictures for us to look at, but then we'll also use technology and a formula to get some more specific intuition about this. And the questions are something like this. If I look at this vector field and this square, drawn in here on the xy plane, the question would be something like, is there more vector field flowing into this square, or is there more vector field flowing out of this square? Or is there as much flowing in as flowing out? Right? And the answer to that question is a number that we would call the flux, the inward or outward flux, depending on how we want to orient it, right? The inward or outward flux of the vector field into this box or out of this box. And in the case where there is exactly as much inflow as there is outflow, we would call that net flux equal to 0. So our overall shape of what we're going to do today is we're going to first think about this question as a macroscopic question that we would presumably have to use an integral in order to compute. But then, just like we did with circulation, we're also going to shift gears and look at a microscopic version of flux called a flux density. Right? We had a circulation density before. We're going to get a flux density today that tells us sort of at a single point, if I could draw this box infinitesimally small, would the vector field be flowing into it, out of it, or would the in and the out cancel one another out? So we get both a macroscopic measurement using an integral and also a microscopic differential measurement that's going to use a type of derivative for our vector field. And then the big finish is going to be, how do those two viewpoints connect with one another? How can the flux density, which is the microscopic version of flux, how can that flux density function tell me something about the total flux through an actual macroscopic closed curve in the xy plane? So the question for each vector field is, given the closed curve that's drawn here, is there more of the field going in or out, or is there the same amount going in as out? And then talk about how whether that answer that you came up with suggests that the vector field is either kind of being created or destroyed or is unchanging in strength within that square. And then in part C, would your answer change if you changed either the size of your square or the location of your square within the xy plane? And those are exactly the kinds of questions where having this vector field analyzer is a really helpful adjunct for our conceptual reasoning. So let me just point out quickly how you would use the vector field analyzer tool to get at these questions. So I've provided formulas for these vector fields for you to use at this step in the process. So the first one has a formula minus x minus y. So I'll put that into our analyzer so that we can look at it. So here's the vector field from part A of our preview activity. And so if I want to see what is the net flux into or out of a surface, I'll want to go over to the line integrals tab. So again, I would use this little secret arrow button up here in the top right to show me the third tab, which is line integrals. This time we want to choose to show flux. Last time we used this tool, we were interested in circulation. And I'll choose box so that I can draw a square inside of this diagram. And so here it's coloring the inward flux as a sort of a blue, a light blue color, and the outward flux is being colored as this pinkish color. And then the net flux is right here, this number that's being reported. So in this particular square, the net flux is negative 3.96. Right. Now, if I want to resize this square, I can use the resize curve button down here. And when I do that, I can just click and drag to make this square bigger or smaller. I can also use the move curve tool to move it to different places in the xy plane. So those are both really valuable ways to engage in the heuristic thinking that's going on in this preview activity as well as in some of the activities that follow it today. Cool. So in the course of this preview, you looked at 3 different vector fields and a variety of different closed curves. Sorry about that, I was muted. In the variety of this activity, you looked at 3 different vector fields and 3 different closed curves and tried to estimate the inflow and outflow of these vector fields from these closed curves. So was there more field flowing into the curve? Was there a stronger field flowing out of the curve? Or did it balance exactly out? And so you predicted that for our first vector field, this one here, it looked like there's more coming out than going in. It seems like the strength of the vector field arrows that are coming out of this closed box is stronger than the tiny little arrows that are coming in. And so the net is a net outflow from the box. If we were to place a blob of ink in the middle of this box and then let it flow along the vector field, the idea is that that ink would probably be spreading out and getting larger in area as it went along. Whereas in our second vector field, it looked like there's sort of possibly more coming in than there is going out. And zoom just a little bit closer in on that to see how, right? And so if I were to place a blob of ink on this square in my vector field, then the ink would be getting smaller, be getting compressed in on itself as it flows along. Meanwhile, this vector field seems like it's just kind of circulating, and there is about as much going in as there is coming out. And so it's not written in this team's write-up, but I think it was written in the other team's write-up here, that the flow into or out of that vector field looks like it should be about balanced, right? There's about as much flow coming in as there is going out, And so we expect that it's situation number 3. And that your answers seem like they possibly could vary if we chose a square that was bigger or a square that was smaller. So as an example to look at that question, let's look at the second vector field here. Well, no, let's look at the first one because it has kind of the easier formula. So this vector field is the vector field x comma y. And if I look at that vector field, x comma y, looks like this. I take and draw in my box up here. And I figure out that, yes, it looks like the amount of outflow from this box, the pink shaded area here, looks like it overwhelms the amount of inflow, which is a little bit smaller, right, the blue shaded area. And so the net is a net outflow. And so according to the vector field tool here, that flux is this number, 5.691, and that would be measured somehow in the units of the strength of the vector field multiplied by the units of length, so the lengths along the sides of this box. And that if I change the size of my box, it looks like the amount of flux is actually going to be changing. Smaller boxes are going to give me less flux just because I have less vector field arrows going in and less vector field arrows going out, right? And a bigger box is going to give me more flux. But what you notice isn't changing in this example is the ratio of that flux to the area of my box. Right? That in this example, at least, it looks like the amount of flux is getting bigger and smaller only because the area of my box is getting bigger and smaller, but that they stand in the same ratio to one another the whole time, and that ratio happens to be 2. So the flux is just twice the area of my box for this particular vector field. And so where we're going with this today is that if I take this box and make it smaller and smaller and smaller and smaller and smaller, then my flux is getting smaller and smaller and smaller, but the ratio is remaining the same. And that ratio is going to be our infinitesimal quantity called the flux density at a single point, right? It's the net flux into or out of a box divided by the area of that box in the limit as the area of that box shrinks down to 0. And so for this example, it looks like that infinitesimal flux would have the value of 2. Right? That appears to be the limit of the ratio of flux divided by unit area as we let the area approach 0. And so at all the different points in this activity, we potentially have different answers with one exception. And that exception was this vector field that was just kind of circulating. And if we test our hypothesis on that vector field, y comma minus x. No, minus is in the wrong place. It's minus y comma x. So that we're circulating counterclockwise. If I put my box in here, you predicted that the flux into and out of that box would cancel one another out, and that's what the tool is telling us here, that the net flux is equal to 0. And that doesn't depend on how big or small my box is. That flux still ends up being 0. And it also doesn't seem to depend on where I place this box inside the xy plane. No matter where it goes, there is as much inflow as there is outflow. And so the flux is the same everywhere, but that's only because the flux is 0 everywhere. Right? And that ratio, right, of the flux per unit area, it seems like at every one of the points here is going to be equal to 0. And so it's that 0-ness here that is responsible for the fact that the flux doesn't seem to depend on the size of the box. And furthermore, it seems not to depend on the location of the box either for this particular vector field. So that's kind of our initial look at what flux integrals are, sort of what they're going to have the ability to tell us. And so the rest of our job for today is to take that macroscopic idea of the flux into or out of an actual closed curve in the xy plane. And for our first step, try to relax the assumption that we have a closed curve and just think about what should flux through a single open curve actually look like. If my curve has a starting point and an ending point, how should I think about what the flux is across that curve between my starting point and my ending point? And then from there, sort of piece that back together into the idea of the flux around a closed curve as a macroscopic measurement, and then figure out how to get down to the microscopic measurement, in other words, the flux density, the limit of this ratio over here, as the area of my curve along which we're going to take the flux approaches 0.